Hi, I'm Ben. I am working in cosmology and up at the Royal Observatory here in Edinburgh. And half my research is done for the Dark Energy Survey, which includes the part I'm actually talking about today. And generally, statistics has been active in cosmology and exoplanets research within astronomy for decades now. Turned Bayesian around 2001. And machine learning is on the rise. So, for example, we have the International Astrostatistics Association now, and for a few years now, the Cosmos Statistics Initiative, which is essentially a one-week meeting once a year. So research retreat of people from different departments to do interesting astrophysics research, mostly at the current bleeding edge of deep learning and machine learning methods. And usually in nice locations. So last year we were in Crete. This year I think it's France. Yeah. So I have a similar slide to Debbie. I'm very sorry about that, I didn't know. So I also did a quick search for machine learning and deep learning in titles and abstracts on the arXiv, but this one is specific to astrophysics arXiv. And as you can see, over the last 5-ish years, machine learning really began to rise exponentially. And for the last 5 years, suddenly there is a lot of deep learning. And when I started my PhD, I was told, yeah, deep learning and cosmology, people aren't really ready for that. Now, most conferences have extra sessions for that. So I thought I would give a quick primer on cosmology, because generally people are interested in it, but people don't want to be confronted with the mathematics, and I don't want to get into that anyway today. So I quickly want to introduce the standard model of cosmology, which is the lambda CDM model, just so that you know why exactly I do what I do. So as you can see in this very bad representation that I drew here, on the far left side you see what we assume to be the Big Bang, followed by, very shortly after that, a period of very rapid inflation, which is the currently accepted hypothesis. After about 380,000 years into the universe, the cosmic microwave background formed, which I will get into later. And after that, we have structure formation, which means that the initial fluctuations that we have in the matter distributions in the universe enabled gravity to pull stuff together, which enabled galaxies to form in the first place. And then around 2000, or new millennium, we found out that the universe accelerated its expansion, which is super weird because, I mean, we had dark matter at that point because you would expect galaxies to fly just apart based on rotation and heat dissipation. But at some point, if stuff goes away from itself, you'd expect gravity to kick in enough to slow it down and then pull it back together. And the current observation suggests that's not the case. So dark energy is essentially our placeholder term for something pressure-like in space pushes stuff apart. And it's one of the main questions that the Dark Energy Survey tackles, as the name suggests. So in the lambda CDM model, lambda is the cosmological constant, which is the energy density of the vacuum of space, essentially our solution to stuff goes apart. And CDM refers to cold dark matter, where cold means slow, but slow with respect to the speed of light. So still not that slow. And generally, we have a lot of cosmological parameters. So there's not only lambda, there are a few others. One of them is omega m, which is the total matter density we have in the universe. So that's dark matter and baryonic matter. Then we have omega b, which is just for baryonic matter. And that's a fancy term to say things that aren't dark matter. So everything we see, you, me, this planet, the universe, or at least the stuff we see. And others are the expansion rate of the universe and the early universe amplitude of density fluctuations, which means the universe wasn't entirely homogeneous. And that is the cosmic microwave background right there in the middle. And it was discovered by accident in the 60s. So two radio astronomers, which you can see on the upper left side, had this thing that looks like a giant ear trumpet. And that's kind of exactly what it is. They had this annoying interference in their signals. And at first they thought it was birds. and they had to scrape a lot of what they called white dielectric material from their ear trumpet. And it turned out to be persistent, and at some point they realized that it was background radiation throughout the universe. And then in 2001, NASA shot up the COBE satellite and gave us the first image. And then later, on the upper right side, you see the construction of the Planck satellite, which is a space telescope. And that one gave us the picture that you see here in the middle. And there's also some ground-based operations going on. I took the BICEP 2 and Keck array because it's such a weird place to park your telescope because it's on the South Pole, or I think now, because of the shift, it's like 10 or 20 meters right of the South Pole. So it's in the middle of Antarctica. And the way that cosmological parameters are estimated is we calculate Bayesian posteriors. The reason that is done is we don't just want to do maximum likelihood estimation, which was done before 2001. Because then we have best fit values, and we have that for one survey, and then we have it for another survey, and then we can calculate the distance between those, but that's pretty much it. But we want to know how well do different data sets agree with each other. So we want the probability distributions per parameter. And also we want to know what fraction of that probability distribution agrees with a certain cosmological theory. So the current status quo is that we start to deal with high-dimensional parameter estimation. So high-dimensional is relative for our own direct energy survey. That's 26 dimensions. Planck and Euclid in the future will have about 100, from what I was told. And the calculation of every single probability takes about 10 seconds or 10 to 15. And if you use MCMC algorithms, you can parallelize them to a degree by using multiple walkers, for example, affine invariant methods, so MCMC ensembles, but still it takes a lot of time. And you need chains in MCMC walkers of a certain length, so that you can actually sample from the posterior. Also, we can't really know much about the distribution, so of course you can assume it's Gaussian because most things are to a sufficient degree. But generally, you don't want to do that, and a lot of the parameter combinations are more banana-shaped anyway. So, the future of cosmology in terms of instrumentation is quite interesting. So on the left side, you see the James Webb Space Telescope, or at least its mirror. The whole thing in space will look more like a ship with that thing as its sail. And on the right side, you see for LST the mirror, or at least the blank for the mirror, on which I think the main researchers sit. So in the hole in the middle, there will be a second mirror, which is kind of a weird setup, but apparently it worked to actually get that done. So as you can see, the scale of telescopes, both on the ground and in space, gets larger and larger, because we want to go deeper and deeper into the universe. And I thought I should mention LISA, which is the Laser Interferometer Space Antenna, because it's such a weird concept, and people often don't believe me when I explain it. So what we want to do in the 30s, and this is planned since the 80s, so it's a large collaboration long-term, is we'll shoot 3 satellites into space to form a triangle, a nearly perfect one, with sides 2.5 kilometers long. And then we shoot lasers between them. So we have a giant laser hipster triangle trailing our planet. And the whole thing will act as a gravitational wave detector. So it's for similar purposes as LIGO, which you maybe saw in the news with the whole gravitational wave detections. But it will be able to probe events that are difficult to detect on Earth. So to come to what I'm actually doing. So I decided to skip the math for the most part and just to explain it conceptually. So we have to calculate posteriors for cosmological parameters. And we can start, or we have from previous experiments in most cases, an initial sample. So that sample might be an extremely bad or rough guess. That's only in the rough ballpark of what might be right. And what we are doing in the first step is to fit a model to these bad samples, or this rough sample guess. And in high dimensions, that's a variational Bayesian Gaussian mixture model, which is essentially a Gaussian mixture model that is able to determine the number of components it has to use based on the data. So you don't have to do brute force optimization. And we follow that step by using a recent extension of importance resampling. So what that does is we take the sample, we then fit a model to the sample, and then we morph and shift the posterior distribution towards the true posterior based on the probability we calculate in the second green step. And we do that iteratively over multiple, usually about 20 iterations. So we have a convergence criterion for that. And the reason we're doing that is that the model fitting is pretty cheap computationally, and the importance resampling takes 10 to 15 seconds per likelihood, but it's embarrassingly parallel. So that way, if we have enough cores, we can compute cosmological parameters and the associated probability distributions extremely fast. And in the end, you get the model itself, the number of samples you request, and their importance weights. And I will show you how that looks in a very short time. So if anyone wants to go into the math in the question time, we can do that. So the primary features of the implementation that we did, so it's an open source Python 3 tool for cosmologists and other people to use. It builds on previous research, for example, by Kilbringer and his team on Cosmo PMC, who also use an importance sampling approach. We were able to implement a working convergence criterion, which you usually don't have for MCMC algorithms, and which we're very proud of. And the whole reason we use truncated importance resampling is that if you take a small number of samples, and 10,000 samples is a small sample in 26 dimensions, then normal importance resampling will get you a few very, very high posterior value points. So it will fit maybe around these 5 points, say, very tight distributions. And then the whole iterative approach doesn't work anymore. And truncated importance sampling is just thresholding that whole thing. We also have built-in MPI capabilities. And this project is actually heavily dependent on NERSC, so we're running that on there. And yeah, we usually have to wait a bit to get the required number of cores. For the final run, we would need about 10 to 15,000, so if you could make that happen. No, we usually have to go with around 1,000 or 2,000. That's realistic. So the tool itself is called Gaussbock, and it's currently available on PyPy. The name itself is a bad German pun between Gaussian and the name for a mountain goat in German. It sounded funny when we came up with it. That's the only defense I have. And the good thing is that it has a bunch of parameters that you can customize, but it only has 3 required inputs, which is your actual posterior function, the ranges for your parameters, and just the number of output samples you want. Everything else is mostly adaptively calculated based on the data you put in. So it's easy to use, and it's also a general parameter estimation tool, so it was developed with cosmology in mind, but you can use it for anything where you have a log likelihood, really. Now, that isn't the full dark energy survey likelihood. That's a truncated Gaussian approximation of it. We didn't run that on NERSC. But that allowed us to prototype very fast. So what you can see in the distributions on the upper and right-hand sides is the yellow distribution is what you start with. And I didn't plot it there, but it's essentially a weird-looking shaggy distribution with a weird horn for the left side one. And it then returns you in the end the green distribution. And if you then weigh that with the importance samples, it also returns. It gives you the blue distribution. And the red one that you nearly don't see because it overlaps so nicely, that's the true posterior. And that's also truncated in 26 dimensions. So hopefully the full run on NERSC will look exactly the same. At least that's our hope. As for scaling, we ran 50 runs of our algorithm on the approximated death likelihood to get confidence intervals and estimates for different number of samples that you take, which also dictates the number of cores you need on the left side. And as expected, you need fewer iterations to converge if you have more cores and hence more samples. And on the right side, you see that it scales mildly exponentially. So the higher the number of estimated parameters or the higher the dimensionality of the problem, the more iterations you need, because the more complex the problem is. For the low-dimensional case, we use KDE because that works better in 1 and 2 dimensions. And I present the first sampling from the Triforce. So what we did is we developed a flat surface posterior distribution to have a very hard to approximate thing to see how well our method would work if presented with a posterior that would be hard to fit with any method. And that will make it into the paper. And shortly before I finish, I want to acknowledge the open source software that we actually used for the whole project. So I don't think I have to introduce Python, NumPy, and SciPy. Most of the prototyping was done in Jupyter Notebooks. The variational Bayesian Gaussian mixture model comes from an implementation based on work by David Bly and his colleagues, and which is implemented in scikit-learn. Schwimmbad is used for MPI parallelization. And that is the German word for a swimming pool, and it's about parallelization pools. So we're not the only people who use bad German puns for their tools. And MC, we use that one. If you don't have an initial sample guess, you can do a very short run, like mosaic approximation with only like 1,000 or 500 steps per walker for an MCMC algorithm. And the logo is the actual name of the published paper. And one of the goals I have in life is to publish a paper and get it through peer review with a similarly punny title. Also, since I probably wouldn't get away talking about astrophysics without showing galaxies, here are some pictures. But those galaxies don't exist. So that's from a recent paper we published, and it's about essentially multi-staged generative adversarial networks to create physically realistic galaxies that follow the same distributional parameters. And at this point, I think I definitely have to end.